Have you ever wondered why the simple triangle hides one of the most important secrets in all of mathematics? Today we're going to discover the Pythagorean Theorem together. Not just memorize it, but truly understand it. That famous a squared plus b squared equals c squared you've seen so many times in class. Stay with us, because by the end, this formula will feel completely obvious once you see it the right way. Around 570 BC, on the Greek island of Samos, one of history's greatest mathematical minds was born. His name was Pythagoras, philosopher, mathematician, and founder of one of antiquity's most influential schools of thought. He later settled in Croton in southern Italy, where he founded a secretive community devoted entirely to mathematics, music, and philosophy. His followers believed that numbers were the hidden foundation of all reality, that everything in the universe could be understood through mathematics. And the theorem that bears his name would go on to change geometry and our understanding of space forever. Before we prove the theorem, let's make sure we understand the star of the show, the right triangle. A right triangle has one angle that measures exactly 90 degrees. That little square in the corner is the universal symbol for it. The two sides that form the right angle are called legs. We label them A and B. And the side opposite the right angle, the longest one, is called the hypotenuse. That's our C. These three sides are the key players in the Pythagorean theorem. Remember them well. Now, here's where the magic begins. Let's build a square on each side of our right triangle. First, a square on leg A. Its area is A times A, that's A squared. Now, a square on leg B. Its area is B times B, B squared. And finally, a square on the hypotenuse C. Its area is C squared. 3 squares, 3 areas. And here's the big question. How do these 3 areas relate to each other? Let's prove this once and for all. Visually, no algebra needed. We draw a large square with side A plus B. Then we place 4 identical right triangles inside, one in each corner. The space left in the center is a tilted square with side C, so its area is C squared. The 4 triangles plus C squared fill the whole big square. Now watch. We slide the exact same 4 triangles to 2 corners. Nothing disappears, nothing is added. This time 2 squares appear in the empty space, one with area A squared and one with area B squared. Both arrangements live inside the same big square. The 4 triangles are identical. So whatever is left over must be equal. C squared equals A squared plus B squared. Let's put the formula to the test with the most famous right triangle, the 3 to 4, 5. If we build a square on the side of 3, we see it contains exactly 9 small squares. The square on the side of 4 contains exactly 16 small squares.
And the large square on the hypotenuse of 5 contains exactly 25 squares.
If we add the 9 red squares plus the 16 green ones, we get exactly 25. 9 plus 16 equals 25. The formula works perfectly. But where do we use this in real life? The answer is everywhere. First, in construction. From skyscrapers to your own house, builders use the theorem to ensure every corner is a perfect 90-degree right angle. Second, in your phone's GPS, the system measures the distance to multiple satellites. By knowing those distances, it calculates your exact position on the map. It's triangulation in space, and its foundation is Pythagoras. And third, in your favorite video games. Every time an enemy detects you or an ability calculates its range, the game engine is using the theorem to measure the straight line distance between 2 points on the screen. So you see, it's not just a formula in a textbook. It's the secret language our world is measured and built with. To wrap things up, let's solve 2 final examples together. First, imagine a triangle with legs measuring 5 and 12. How long is the hypotenuse? We start with our formula. We substitute A with 5 and B with 12. Next, we calculate the squares. 5 squared is 25 and 12 squared is 144. Now, we add them together. 25 plus 144 equals 169. To find C, we take the square root of 169, which is exactly 13. So the hypotenuse is 13. Great! For our second example, what if we know the hypotenuse is 10 and one leg is 6? Again, we substitute the values we know into the formula. This time we need to find b, so we rearrange the equation. B squared equals c squared minus a squared. Let's calculate the squares. 10 squared is 100 and 6 squared is 36. The difference is 64. Finally, the square root of 64 gives us our answer. It's 8. The missing leg is 8. And that's it. Now you not only know the formula, but you've seen why it works and how to apply it. So our journey comes to an end. We started with a simple question about a timeless formula. We traveled back in time to ancient Greece, understood the parts of a right triangle, and we proved the theorem visually, seeing how the areas of the smaller squares perfectly equal the largest one. We saw it in action with the 3, 4, 5 triangle in the real world of construction, GPS, and even video games. But this theorem isn't an ending, it's a gateway. It's the heart of trigonometry, defining the fundamental relationship between sine and cosine. It even gets a mind-bending upgrade in Einstein's theory of relativity in space-time itself. From the smallest pixel to the largest galaxy, this simple idea is woven into the fabric of reality. If you enjoyed this visual exploration into the world of STEM, and you want to see more animated adventures, please consider subscribing. Tell us in the comments what to animate next. Thanks for watching.